Okay, now let's look at some examples of the system call that I have prepared for you. First of all, you can look up the list of system calls conveniently online. So I don't think there is a convenient way of looking at all of them in Linux with their number, but you can find it online. So as I said, you can look up which number corresponds to what system calls. Okay, but anyways, let's look at some codes. So the next system call that I want to show you is called nanosleep. So I have this assembly program here. Again, to look at the manual of the nanosleep, we can see that it requires two parameters here, right? So this is this wrapper or the C wrapper for the system call. So it needs two parameters and returns an integer. By looking at the two parameters, we'll realize that the two parameters that we pass are pointers or address or memory addresses of two structs. So the two structs are defined, or each struct is this time spec struct, and it has two essentially long integers or two 64-bit integers inside that struct. And what this system call is supposed to do is supposed to sleep for the amount of time that is described in the first struct in nanoseconds, and this struct is divided in two parts: how many seconds you want to sleep and how many nanoseconds you want to sleep. If you're woken up before your sleep duration is done, the remaining time will be replaced inside this second struct. If you're not woken up before your time is up, then I guess that would be 0. It could return an error, and you can read about what the errors are and etc. in the manual pages. But we want to use this program in assembly, so let's look at our assembly program over here. So we have supposed to have two structs of 64 bits. So each struct should have 128 bits. So we have two quads. So the first one, if you recall the manual page, the first 64-bit describes how many seconds. So we want to sleep 1 second, and whatever this number is in millisecond, which this number roughly, I guess it is roughly 2/3 of a second. Okay, and the second struct is how many remaining time. So that's the second struct. Okay, so remember that we have to send the first parameter is the starting location of this struct. So it should be essentially this address, and the second parameter should be that address. Okay, so let's set it up. By looking up the numbers, you will realize that nanosleep has number 35, so we put 35 in the RAX, which is the system call number. The two parameters need to be passed by registers RDI and RSI. So we put the value of, or the starting address of the first struct, which is S time, in the register RDI, and we put the starting point of the second struct, which is the remaining time 1, in the register RSI, and then we do the system call, and finally we do the exiting, or we exit the program using this exit system call. Okay, so as before, we can compile this like this: assemble, link, and then execute. So that doesn't produce any output, just waits for a while. We can time this nano program through this time command, and we'll see that it essentially runs or sleeps for the amount of time. I guess the time has rounded up to 1666, and I guess it probably takes a little bit longer to run the program and to exit and stuff. So we get roughly what we wanted. Okay, so that concludes the nanosleep system call. Wait, I forgot. I could also run it with strace, and we'll see that we get the nanosleep system call, and everything is normal. Okay, so nothing too fancy. It's a very nice system call, and so the thing is, in Linux, it is not so easy to have system calls or use system calls in short and sweet programs, but I could find some fun system calls here. So let me show you this shared C program, which is trying to create a shared memory. Okay, so I'm not going to use assembly because I need to allocate memory, although do stuff. So therefore, I'm just using the C here. Here we're going to be using two system calls: this shmget, shared memory get, and shared memory create attach. So first of all, you can, as always, whenever you want to learn about the system call, you should read the manual pages. The manual pages are they're usually very nicely written, so it should be possible for you to understand it. So this system call has 3 parameters: a key, a size, and some flags to how this shared memory would work. Okay. So key is, I've defined some random key here. The size, what I want is to be roughly 1 kilobyte in size, and then the flags. Okay, so this flags I'm going to explain what these mean. Okay. So here, create new segment. So this is what we want to do in this system call. We want to create a piece of memory that could be shared potentially between different programs, right? So we want to create this, and we're also setting it up with some permissions. So this is basically what I've done over here. Right? I'm not expecting to get any errors because I'm not asking for a lot of memory. So this error checking code I'm not expecting it to be executed. Then we do shared memory attach, man shm attach. And again, before using it, you should read this manual page, and then it explains exactly what it does. But basically, I'm essentially running this with quote unquote normal or default parameters, so I'm not doing anything fancy with this. I'm just attaching it to a piece to an actual physical memory, or Linux will do it for me, and I would get a starting address. So by doing these two steps, I have managed to allocate a chunk of memory. You might be thinking this is too many steps. I could have just done malloc or malloc, but I have received a starting location or a starting pointer to this 1 kilobyte of memory that I've allocated. Then I will cast this address point, which is a pointer void star, a generic pointer to an int star, so and a pointer to an integer. So 1 kilobyte of memory should translate to 256 integers because each integer is 4 bytes. I'm not using it all. I'm just changing or initializing the first 10 integers to be, say, 2 times I, from 0 to essentially 18. Okay, using this for loop. And finally, in an infinite loop, I am printing the starting location of my integer array, as well as the values of the first 10 numbers in this array. Okay, so I set it up from 0 to 18, and I'm not expecting them to change right now. So this while loop should constantly print exact same numbers. Okay, so let's run this. Actually, I think I have shared C. Oh, so shared C. Okay, so let's run it. Yeah, so this is I expected to get an output like this. So it just prints same thing over and over again. Okay, so it's nothing too exciting right now. So now let's look at the other program that I have created. So this is more or less the same program. Okay, we've seen it before. It annoys me. I have a typo here this time. Except this part is different. So what we're doing here in this part is that we're incrementing all the first 10 numbers in the array, but we're also printing the address of the array. And then we're waiting for some key, for the user to press key to exit. Okay, so let's compile this. Shared A. Whoops, I typoed. It's okay. Shared A. Let's see what happens. As you'll see in this other terminal, all these numbers that this program was printing got incremented by 5. So in other words, this program managed to write to the same physical location as this other program. So that's the first interesting thing that we can observe. The second interesting that we can observe is that these memory locations are different. So the starting location of this array was this number, ignoring the zeros, ending in 7FE. But this one ends in C17. Okay, so these two virtual addresses are the same. So in this case, we have a case of two programs that are writing to different virtual addresses, but the two different virtual addresses are translated to the same physical locations. So they are literally sharing a physical location. Okay. If I run this program again, I will be getting a completely different virtual address, but nonetheless, all the values on the right-hand side will be incremented by 1. Okay, so let's try to do something fun again. So share. Okay, so I have these two processes. Okay, let's look at how they set up in memory. If I do pmap of the first program, I'll see that in this thing I have this chunk of the memory as like PMAP marks it for me as being shared. Okay, and it has some shared ID. And if I look at this address, I'll realize that this address is exactly the same address that this other program is reporting. So I can see that this program is virtual, this program is set up in the virtual memory, and it has a block of memory called shared, or marked as shared, as starting from this address. If I look at the second program, I should be getting that number and the more or less similar structure. Okay, so again, this other program also has the same amount. The other interesting that we can observe is that the size of this memory is 4 kilobytes, even though I asked for 1 kilobyte. Why is that? Well, it's because the smallest chunk of unit the OS can allocate is 4 kilobytes. So even though I asked for 1 kilobyte, I got 4 kilobytes anyways. So if I want, I could exceed the limit of my array. I could write beyond the 1K limit that I asked for up to this 4K limit. Okay, so this is all allocated to me. And again, we see that the starting or the address that we get here for the starting location of this chunk of memory in virtual memory matches the address that my program was outputting. Okay, so this helps you also see how shared memory could be used. I mean, obviously, this example is not a very good example because I would allow any program to write to my memory location. But this is, but you could have more control over, some control over how these security measures of this thing. So with this, what shared memory in this case offers is lots of things. For example, you could have multiple programs that could cooperate to solve a problem or to do some computation. By having a shared memory, they could pass information very easily among each other. Or if you have, if you want to load something that you want to be read-only and shared by multiple programs and not use physical memory, you could do this, even though Linux will typically do the optimization for you. But this is an explicit way of making sure that programs actually share some amount of physical memory. With this, I think we can wrap up the discussion of the system calls and the examples of it.